Thank you. I would like to thank the organizers. I would like to also thank the most important people in the room, the audience. Like the other Mihai yesterday, eventually, okay. I'm reporting on this work with Mr. Lozovano about local positivity of some polarized free folds. There are usually going to be free folds that you construct starting from curves. So product of curves, product of Fulger, and so on. So the very general setup is that X is a smooth projective variety of dimension n. First, and we take the point and L an ample line. So then the pair Lx would be the polarized in this case. And then we want to quantify positivity, and there are several ways to do this. So local positivity. So Ls or around. Even though it's called local positivity, it needs a projective variety around it or something sweet. So it's sort of local global positivity. So it's encoded by some invariants. So one of them could be the Sechadric constant. But before I can define this, I need to blow off the point. So we go up the smooth point. Okay, and we also define L2. It's going to be on the block. The pullback of L minus PT. It's allowed to be an arc divisor. I'm identifying line bundles with divisors and then also moving to real coefficients. So this is the Freeman. T greater or equal to 0, such that LP, we could say ample or MEV. So if you put MEV, it's actually a maximum. If you put ample, it's an actual supremum, not a maximum. So this is also called the Sechadric constant. Mentioned yesterday as a bad boy by Schiller. Okay. Then we could have the width.
Does this have a differential geometry, complex geometry?
Yes, but I don't know any of that. So there are other interpretations for the Sechadric constant in terms of the attacking. Is that your question?
Like until there is codiagonal theorem with until if it has a metric, is it similar?
The net thing?
Similar for Sechadric constant, is it some similar differential interpretation?
I'm sure there is. So this is the suprema, T greater or equal to 0, where LP is big, or what do they effective? So everybody knows what ample is. Ample is limit of ample. It's the narrow separate space. If it flows up, the ample cone has net cone, and if the divider has per-chain class. In the next cone, we call it net. It's also the same as having negative intersection of all curves. This is the lead. I've been calling it the defined variant of at the point. I'm not sure that's accurate. Okay, so what's pseudo-effective? It's like net, but you close up the effective cone. That was also mentioned yesterday by Chris. And the big cone is the interior of the pseudo-effective cone. Okay, this was the width also came up in the talk of Berger yesterday, but I think it's a similar concept and something that's less that I haven't seen studied before. Except if it happens to be equal to a successive minima of L. So this is the suprema, T greater or equal to 0, where LP is functions in a linear system without fixed pictorial control. So it makes us for dimension 2 base locus, but not for dimension 1. Okay, I don't have a name for this one. Okay, and these are numbers. There is also a function that's of interest. T goes with the volume of the. Let's define this volume. So if D is a divisor or line bundle, and our n-dimensional x, then you define the volume with the limit as n goes to infinity. The dimension of the space of section of MD, or for line bundles, you put L to the tensor power m over m to the n over m factorial. This is a normalization factor, and it makes some computations nice. So if is unfollowed definite, then we have the volume of E, the self-intersection number. But the problem is more delicate in general. So this volume function could be something big of interest. It has nice behavior up to the Sechant, from 0 up to the Sechant constant, and it has trivial behavior after the width. This is supposed to be the t-axis. This is 0, and let's say here we have the Sechant constant. Say here we have the width. Then after the width, the volume is 0 because we have no sections. Take the limit up. And from 0 to the Sechant constant, the volume is very big and confusing. It's the self-intersection. This ends up being the self-intersection of L minus T to the n. Anyway, the middle, even between the Sechant constant and this movable invariant, the volume is unknown. Okay, and then there is the ultimate measure of local positivity, which is the infinitesimal internal composite body. It's supposed to be the very general infinitesimal composite body of LSA. I do not want to define this invariant. It's a valuative object. It's a convex body of dimension n sitting in the non-negative origin in Rn, where n is the dimension, and it encodes the is how wide the body is. The Sechant constant has to do with how big of a sort of a simplex can you put in here, starting from the origin. We'll see examples how it encodes the volume function. And I guess eventually one will show that it also encodes this invariant. Okay, so let's see. Since I do not want to define this object, we're going to focus on how we compute volumes in the non-net case. Okay, so the answer is sort of easy on surfaces. Then we have a Zariski decomposition. where P itself is net and is effective. So an actual linear combination with non-negative coefficients of curves. You may have to use Q coefficients. And it's not, I guess, the official definition of the direct decomposition, but this property is equivalent to it. So the volume of P is the volume of the positive part, and the positive part is net, so it's the top self-intersection of P. Now, if P is actually effective, which is what we would usually want, if it's not effective, then if it's purely pseudo-effective and not effective, or if it's not pseudo-effective at all, then the volume is zero, so we don't care. So we usually assume that P is effective, and then if you have an effective representative, then there are algorithms for computing the direct decomposition, so the problem is not that bad. Okay, but how about? Actually, let's see some examples in practice. So it will set us up for the problem that we want to work on threefold. So let's take C. Let's say it's a smooth genus 2 curve. Then associated to it, we have the Jacobian of C that I'm going to call J. And this is divisors of degree 0 on the curve. And we have factorization theta, and will be useful. And we want to understand, all of these invariants of the field.
You need to move it further down. Further down. No. Yeah.
An interesting curve. So first of all, we have the other Jacobian embedding of C, but we also have the image of the curve under the multiplication by 2 and the Jacobian. So let's give a name to this graph that I usually want to call mu, but mu is also the width. So let's call it gamma, and hope I don't have to use it again, or add something else. So over here we have the other Jacobian embedding of C, and its image, let's denote it R. Now, when we blow up the origin in J, when we want to compute local positivity on a abelian variety, the point doesn't really matter because we can translate to any other point. But let's say this is the blow up of the origin. Okay. Then when we look at the strict transform of R, it becomes isomorphic to C. So R has a singularity of multiplicity 6 at the origin. That's because the first points of C get the origin. Okay, I'm keeping a little bit. Embedding this, but after multiplying by 2, it's sort of the 6 bars points all go to the same point. Okay, so it's isomorphic. This is more reducible. So it implies that R bar is a pseudo-effective zone of J bar. And you see that up to multiples it tells us that mu, the width, I guess at the origin. So this is going to be 6/4, which is 3/2. Sort of by duality. It's not really by duality because we don't know that we're in the situation of a two-dimensional Neuron-Severi space. If the curve is not, if the curve is spatial, it's not. Work here, and on surfaces, the Fisher constant is the net boundary is the same as the movable boundary. And the infinitesimal Newton complexity that has not defined. And that is go. Okay, so this is the infinitesimal Newton complexity. Okay, and if you're wondering about the volume function, so if you give a value between 0 and the width, let's say t0, then the volume of LT is the volume of the slice to the right. And it's also general in all dimensions, so this area, our dimension is to be volume. The normalization factor, so it's probably 2 or half of, so what's the area of this? So the area is 1, and the volume will be 2. So the area will be 1 half the volume of LT. And now if you're wondering where do density decomposition come into the picture, they come into the picture of figuring out where this height is. So for instance, this height over T0 is the positive part of the 0. So this intersection number is this height, which allows us to compute the Newton value in this case. Okay, now let's also look at the situation of a product. So let's say if you want to compute. And then which is equivalent to 1 plus d2f2, where d1 is, let's say d2 is greater or equal to d1, which is greater than 0. And f2 are fibers over c1 and c2. So we call this an ample polarization of box product type, because it's going back something ample here and something ample here. Okay, then one thing work out, but if you want that way, and again, because it's a surface, that the width is the trunk, you want to write this, and then you can so 0, 0, d1, d1, d2, d1, and this is d1 plus d2, 0. So this is this tells you the formula of the volume of LT, and again you would use the density decomposition, which surfaces are very explicit for all LP. There is the confusion to figure out that it's upper part of the trapeze. Like the same type of formula is here. Okay. So surfaces are relatively easy. How about threefolds? So what happens on threefolds is that we know that the compositions in the classical sense. Have different rely on movable divisors more than they do on the divisor. Okay, so we have different divisors. There is gamma sigma diversity composition. So this writes B of pseudo-effective divisor as again the positive part. Well, now this is still effective, but now this is movable. Unlike the case of surfaces, you might actually real coefficients now, but we still have that the volume of D is the volume of D sigma D. It's just that for movable divisors, we do not have a simple formula for computing the volume like we had for net by taking the total intersection in the classical. And then what do you do in general? Well, you're going to introduce a new type of intersection theory, which can either be defined as a movable intersection product or an intersection theory of D divisors. So what you do is you look at all birational models. So this is a birational morphism. And then you consider the gamma sigma decomposition of the fullback of D. And you look at the positive parts. As you vary all the records. It turns out that this is a direct system. Directed system for push forward. So what does this mean? For instance, if I push this down all the way to X, then the positive part here pushes to the positive part of D in this sense. It's not usually true for pullbacks. So if I pull this back, I'm going to get this part, but usually something doesn't need to be. So this type of direct system for push forward is also called the divisor. In the sense of Schoeffer-Roll, where you consider all these morphisms, the fact that this is useful in every so-called incarnation, so for every external, because this is, I mean, the sigma of anything is movable, it makes it a net B divisor. And then for net B divisors, you get that the volume of this is equal to, so let's call it B. So let me put double parentheses. Number, and you can also write it here, and then you can also write it as sigma of B again. So this angular bracket is a removable intersection product. And this is an intersection product of nested divisors. So I'm not defining this, but I want to emphasize that it depends on considering all birational. They're all subsets. And then I have some room here. So the third situation is, so this is difficult to compute because it considers all birational. Situation is, doesn't always exist. So if there exists a birational model such that the positive part of the fullback of D happens to be met, then somehow for higher birational, so further to the fixed middle, the positive part becomes compatible also by fullback, and then this incarnation, this model determines everything. Volume of D is the volume of the fullback. I didn't mention this, but volume is a birational invariant. The volume of the positive part of those intersections, because this now is assumed to be met. So this is a big if, but it's great if it exists, because if we can actually explicitly compute this, we can usually also a birational positive Carbamanta. Moriwaki. Oh, I'll write BCKM for short. Okay, so we'll see that what some yeah.
So if I could go up to that.
Birational morphism. And then
is the decomposition compatible with that directed?
what did you think?
So basically,
this is a direct system for push forward.
and can,
I guess I didn't.
sorry, I meant, can we talk about, or is that what you are saying, that we can talk about the ISP decomposition for B divisor?
Yes, I guess at least for Cartier divisors, which are ones that are determined in some incarnation and with some assumptions for more of them.
We can talk about the ISP decomposition for Cartier B divisor.
Yeah. I didn't mention, but the decomposition the surface is just the usual decomposition. Shooting points in general is not supposed to be deep. There are examples of Cartier divisors, like a canonical class and some variety with irrational volume. We're going to focus on dimension 3. And the grouping question is compute computing infinitesimal Newton control body for the polarization. At the origin or any other point, it doesn't matter ideally for all genera, but the question is pretty difficult for dimension grade for genus grade or equal to 5. So like I mentioned, these guys encode invariants such as the Seshadri constant, and the Seshadri constant is not known for high genera, so maybe this computation is not super feasible in those cases. But let's look at n equals 3. So this will be a long theorem because it's a parallel theorem together. Say E is a smooth quartic curve. So a smooth quartic curve is a non-hyperelliptic genus 3 curve, and we know about quartics that they have 28 tangents, which means that you expect these 5 tangents to meet the curve in 56 points. So we ask that those points are distinct. Then so we can compute our invariance. So the width. So if the point doesn't matter, I'm just going to write 3 of theta. So this is 2. And it's represented by the quick form of taking the image of the difference map from the curve to itself. So C minus C sits in the Jacobian, its divisor is a form OC of x minus 1. Then we take the strip transform. So this surface ends up being a numerical class 2 theta minus 4e. So that means that C minus C has multiplicity 4 at the origin. The reason for that is that the canonical embedding of C is a particle for recovering that. So because of these 2, when you scale by 2, you get theta minus 2e. Okay, and this happens to be a negative in a sort of Nakayama sense. Okay, the Seshadri constant also follows from this and ends up being 12/7. I'm not going to say what's represented by because it's not represented by something nice, it's rather obtained by duality. Okay, and represented. This is seven over 4. And this is represented by the image through the multiplication by 2 map of the symmetric product of the curve that is C plus C. So we take C plus C in the Jacobian. You might have to translate by a divisor of degree 2 to make it of degree 0. Okay, and you take the multiplication by 2 map on the Jacobian, and we're going to close this up. I mean, take strict transform, and this ends up being a class. This one has numerical class 16 theta minus 28. The reason for the 28 is that if you look at the tangent form of this, which tells you the multiplicity at the origin before taking the strict transform, that tangent form is the union of the 28 bitangent lines. Okay, and I can also give the infinitesimal Newton of inequality. So this is the tetrahedron. Because that's the width is 2. It goes up to 1 over 7 0. This has to do with the Bichat constant, and this value over here will be 7 over 4. These boys are not really stored.
Only the very lower end.
Yeah. 7 over 4. 7. Even Tagaromo wasn't made for yet. It probably has to do with, in general, we'll probably observe something similar for muon tripoles. So in this case, it's a tetrahedron. Again, you can compute the volume of LP by fixing the point to 0 and taking x. That's this coordinate being and volume here is x, so it has to do with the volume of LP0. And it needs to be normalized. So before we had 1 over 2, now we're going to have 1 over 6 because 6 is 3 factorial. So the point of this theorem and the computation of the theorem is that we can compute birational decay decomposition for all the divisors. So I mentioned the block when I mentioned the idea. That's one of the cases that we completed. Another case that we completed is the case when, so similar to the one that I raised, no, similar to that one, the product of curves. So these are curves of any general, and we look at this is their product. And again, we take a polarization of form D1 and 1, D2 and 2, D3. where these are in increasing order. If we call it non-decreasing, okay? And so we can always achieve this by rearranging the factors, so it's not a big sensation. Okay, so let's take B1. The movable boundary is B1 plus B2. And the width is B1 plus B2 plus B3. We can also describe the infinitesimal Newton control body, but it will take so just restricts to the simple case where the di's are all equal to 1. So if all di's are 1, then we get a tetrahedron that's even easier than that one. Wasn't very accurate. If the di's are not all equal, then we do not get a simplicial object, although we do get a polyhedral infinitesimal Newton control body. Okay, so what happens in this case is that we also get explicit representatives here and here, and they have to do with straight transforms of sorts of coordinate planes when you look at products of some pair of these curves, and you take the straight transform of that product that passes through X. Okay. Another type of product case that we will that of a curve with a Jacobian surface. See the curve, and these are genus Q curve. And X is C cross the Jacobian B. And we look at the general cross product type divisors. We have a family of them now. LS, which is S times the fiber. I guess we should pick a point. So this is the fiber of the projection over the C in the curve C. And 1 minus this. Set up. This is the fallback of the principal polarization here. So it's a small simplification, so fallback set up in the Jacobian. Okay, I will not be able to draw them. Okay, I'll tell you the result of the computation. Or the constant. Movable boundaries. This is the minimum of 4 over 3. It's 1 minus this. The movable boundary is the minimum between 3 over 2. S and the 1 plus 1. Plus 1/3 this. So this 4/3 and 3/3 Jacobian surfaces. And when okay, and one is on a simple body, and the volume function must easily describable. How are we doing? Is this 50 minutes or not? So what are some of the proof ideas? Of course, we will compute the composition. Maybe you don't get it that detail with the computation of the infinitesimal from a simple particular size. And not going to fit the slide. Maybe this is the idea. As we've seen, we construct interesting curves and surfaces. On the block, I mean on the, I guess on X and X bar. Okay, and then we're trying to use them to identify, to compute invariants like the width and the movable boundary. Okay, construct the PKM decompositions for all LT. In the last case, it's actually an LST. Okay, so how do you do this? Well, you compute the Nakayama schema decomposition. You actually do it. That's a step. And then you try to understand why the movable map. And it's usually because of some curves, and you blow them up. And you continue doing this until you're fortunate and the positive part becomes net. So this is blow up until so you're going to blow up curves that are going to be smooth curves, and you can understand the exceptional divisors in terms of the normal bundles of those curves. If you're wondering what the vector bundles are, they're the normal bundles of curves in this case. For some reason, they happen to always be split. So they're direct sums of line bundles, and then the positivity on these. Positivity on the exceptional divisors of these blocks. and on the strict transforms of the interesting surfaces. So it turns out that this step over here of blowing up until something becomes net usually has a test case, usually has a model case, which is the divisors that represent the movable boundary. So we're trying to make the strict transforms of that net. So that seems to involve some hidden computation of some multiplier ideal. What we do over here, when we restrict to these interesting surfaces, some of them, I'll list some of the ones that show up, and we'll see that some of them can be complicated. What we're doing is we're trying to follow a simplistic algorithm for case one. The surface is the blob of P2. P2 being the exceptional divisor. We blow it up in points and further blow up in 56 infinitely near points to those 56 points. The divisors that we work with are quite symmetric. So these numbers are not that as scary as they look. So that's case one. In case two, so that was the product of 3 different curves. What we're looking at is just a blow up to 6 non-collinear points of P2. And there we explore the fact that this resolves the Fremont form to understand positivity and diversity composition. And for case 3, we're looking at the blob of C cross D. So we fix the point E, and then we look at the cross points. The branching or ramification, I never remember which one is supposed to be on D for the hyperelliptic map of D2 to P1. Okay. Like I mentioned, the blobs try to make the movable part. They also try to compute some diversity decompositions of restrictions of LP to these surfaces. And there is also combinatorics in this block. So where is the combinatorics? We also leverage the combinatorial. Gamma inverse of C plus D. I guess this would be the case in case 1. So C plus C happens to be the theta divisor in the genus 3 case. And we call that by the multiplication by 2 map. And it becomes a union of 4 translates of C plus C. But that the gamma is definitely 64 to 1. I forget if 64 is the actual number of translates because the primage of 0, which is the tutorial point, also shows up many times, like 8 times on C plus C. Okay, so we also leverage combinatorics of trying to describe this primage explicitly in terms of translates by origin and the way those different translates intersect. So part of the blowups that we do at first seem to try to make this divisor simple. You have to be trying to make a log resolution, or part of the way making a log resolution for this. Let's see. I think it's to tell you what happens in the other cases that were. This is work in progress. I did not tell you how the blowups look like for the BCKN composition. Maybe I'll describe something. So for the case, well, the 56 distinct bifunctions. So of course we blow up the origin because the question is actually on the blow up of the origin. Okay, then we blow up the different forms of a curve R. So that's R. So R is in the Jacobian. So it's degree 0 divisors of this form. So x minus x prime. So this is the curve, and the situation is that there exists a point y on the curve, such that when you take the tangent with that point, it intersects in 2 points x prime. So this is a known curve. It's known as a Seshadri curve in the Jacobian in this case, meaning it helps with the computation of the Seshadri constant. It can also be seen as, so it's also gamma of some curve. So in this situation, we would be looking at OC of x plus y. And I guess we want to subtract like a degree 0. So this is a curve, the x and y are as in the situation, it's just that now we're looking at the tangency point, whereas here we were not looking at the tangency point. Okay, and the nice thing about the 56 different bitangency points is that this guy is smooth. The other case is when you have exactly 55 distinct bitangency points and you have to make that's what I want. Okay, and then we need to blow up once more. So let's say this is the exceptional divisor with exceptional divisor G. Then we need to blow up our twiddle, which will be G intersect with the strict transform. So this C minus E is in J, with a bar is in J bar, and with a twiddle is in this blow up of R bar. This is still a copy, and this one is still a copy of C. So it's sort of blowing up the origin, blowing up the copy of C in the blow up, and then also an infinite linear blow up of the curve again. And when you do all these, then you obtain simultaneous BCKM decompositions for all LCD. So the hardest case is the product of C with a deforming, so the ones that we did. In that case, we need 7 blow-ups. And the product of three curves is pretty easy. We blow up the point, and then we blow up sort of coordinate curves through that point. So there will be copies of C1, C2, C3 that pass through the point. You look at the straight transforms, you blow up those. And we expect that to generalize to the product of curves. And in the hyperelliptic case, which I didn't notice, which I didn't mention, it seems that we need infinite meaningful. So we have an explicit infinite sequence of blobs that start alternating between two curves. So it blobs a curve, then it blobs the straight transform of another curve, then it blobs the straight transform of the first curve again, and so on to infinity. So it seems that that case is actually not a BCKM decomposition, but an actual D divisor decomposition. But it also seems to be confusing.